So here's the question I posed, and let's talk through it. So I told you that the drivers are maintaining a constant following distance, and that means the car density is constant. In particular, it's the same in the wide piece of road as it is in the narrow piece of road. But the other thing that has to be the same is the car current. If there's no buildup of cars here, and assuming that cars are neither created nor destroyed, then the car current in the wide piece of road has to be the same as the car current in the narrow piece of road. And so now we see that since n, the number of lanes, is larger here than here, to compensate, V must be larger in the narrower piece of road. In other words, the drivers have to speed up as they enter the narrow piece of road if there's to be no traffic jam. This, in fact, is why traffic jams happen at narrowings of roads, because often the drivers cannot or are unwilling to speed up in the narrower piece of road, and they may be unable or unwilling to reduce their following distance as they go into the narrow part of road. Current is nowhere near as orderly a motion as something like musicians in a marching band. We create current by creating an electric field inside a conductor, and that electric field accelerates the charge carriers. However, the charge carriers also carry out very frequent collisions with the atomic cores in the metal or whatever conductor this is. So the motion is essentially random. If we think about one electron in a metal, it is going in something like parabolic paths because of the electric field. However, it's frequently colliding with atomic cores, and each collision randomizes its velocity. The result is what's called a random walk. And so while the electron generally drifts in the direction opposite the E field, it is a very slow drift, even though the actual speed of the electron is very large. So let's use this idea of this random walk of an electron moving through a metal to find how the average velocity of electrons in the metal depends on other things. First of all, realize that in between collisions, the electron's acceleration is uniform if the E field is uniform, and so we can use our old friend uniformly accelerated motion. In particular, what I mean by this delta t is the time since last collision. And we know that the acceleration can be found from the E field. And that q is just negative e, and the m is the mass of the electron. Now comes the slight trick. Realize that all we really want is an average velocity. And so we are going to average this over all of the electrons in the metal. There are lots of them. And so when we say that the average final velocity is going to be all of these things are constants except for the delta t, which will vary from one electron to another at any given time. And the key thing to realize is that after colliding with atoms, the velocities of the electrons are randomized and point in all directions. And so the average post-collision velocity of the electrons is 0. And so this average velocity of the electrons in the metal is what we call the drift velocity. And we call this average time since the last collision tau, the collision time. Normally, we don't really care about the vector nature of this. We know which way the electrons are going to drift, and so we will normally just talk about the magnitude of the drift velocity. So now we have an expression for the average speed of the electrons in the metal, and let's suppose that we know the density of conduction electrons. In other words, how many conduction electrons there are per unit volume in the metal, and we'll call it N. Then we want to know now how many electrons pass through some cross-section in a time delta t. Well, since we know their speed, then we know that in a time delta t, they're all going to go a distance vd delta t. And now that means that all of the electrons in this volume here, vd delta t long, with this cross-section of A, that volume contains all of the electrons that will pass through this area A in the time delta t. And so we can now write the number of electrons passing through must just be the conduction electron density times the volume here, and so that is just this. And so now what we mean by the electron current is the number of electrons per unit time. We're simply dividing by delta t, and we're left with n VdA. And notice that that has the expected form that we know we should get with a flux. It has a density, it has a speed, and it has a cross-sectional area. So now we have an expression for the drift speed and an expression for the electron current in terms of it, and so we can put the one into the other and get a final form for the electron current like this. And I've written it split up this way to separate out this part, which is all material properties, from this part, which is to do with the geometry of the wire or whatever the conductor is, and this part, the E field, which is something that's perhaps directly under our control based on how we connect this up to a battery or whatever. In particular, note that there are these quantities that you might think are rather difficult to know: the electron density and the time between collisions. And these are difficult to measure, but have been measured, and you can often look them up as tabulated values for a given metal. I think the most surprising thing about all of this is that the collision time is a property of the material. It depends on temperature, but what it doesn't depend on is the E field. You might expect that as you increase the E field and the drift speed of the electrons gets bigger, the time between collisions might decrease. That would make a certain amount of sense. But it doesn't. Why? Well, we can get an explanation if we just calculate the typical drift speed for electrons in a copper wire. Let's say we take a 1 meter long copper wire and we connect it to the terminals of a 9-volt battery. Never do this. The current through this wire could be large enough that the battery would overheat and burst into flames. But we're going to do it anyway as an upper limit on what sorts of drift speeds we would see in a copper wire. So with this, we now know that the E field magnitude is just going to be our potential difference over the length of wire, and so that's just 9 volts per meter. And so we can now find our drift speed. And we get about 4.4 centimeters per second. And remember that this would be a ridiculously huge current. Typically, we see drift speeds that are more like 10 to the negative 4 or 10 to the negative 5 meters per second. However, you can, with physics that we don't know in this course, estimate the typical speed of an electron in a metal. This is not the drift speed, this is its thermal motion. And that speed is typically of order 10 to the 5 meters per second. And so in other words, the drift speed is so ridiculously tiny compared to the speeds the electrons are going that it just makes no difference. And that's why the time between collisions does not depend on the electric field. It's hard to picture that motion of electrons, and so maybe it's useful to go back to the car analogy. What if cars moved the way electrons do in a metal? Well, this would mean you would get onto the highway, and you would be executing very fast random motion. And the highway is full of, say, concrete pylons that you are ricocheting off. And so you are ricocheting off these concrete pylons, moving extremely fast in between. And by extremely fast, I'm going to say, suppose it's about 3,000 kilometers per hour. And now, over time, your average position gradually drifts down the highway so that sometime later you're at a new average position, still zipping around between the pylons, ricocheting off them at 3,000 kilometers per hour. And your drift down the highway is such that if we use the same ratio of orders of magnitude as in a metal, it would have taken you about 10 hours for your average position to move about 10 meters down the highway. Well, let's check your understanding again. So here we have a wire with a thick section and a thin section and current running through it. And we're going to compare the drift speeds, V thick and V thin, the electron currents I thick and I thin, and the electron densities N thick and N thin. And you probably have a sense that there's some difference between them in the two sections of wire, so which quantities are different?